All right, today we are going to tackle a statistical puzzle that trips up almost everyone. I'm talking doctors, scientists, you name it. But if you stick with me, I promise by the end of this, you'll have the master key to solve it. And it's going to help you think way more clearly about risk in your own life. So let's just dive right in. So I want you to imagine this scenario. You go in for a routine screening test. It's for a pretty rare disease. The test, they tell you, is 95% accurate. A few days go by and the result comes back. It's positive. So what's your first thought? I mean, is it time to hit the panic button? Now, your gut reaction, like pretty much everyone else's, is probably something like, oh no, a 95% accurate test means there's a 95% chance I have it. But what if I told you that gut feeling is way, way off? That feeling of certainty, it's actually a really powerful statistical illusion. To really solve this, we can't just fixate on that 195% accurate number. We need a way to think, a framework for updating what we believe when new information, like a test result, comes along. And that whole framework is built on a concept called conditional probability. So, what the heck is conditional probability? Well, you'll see it written as P of A/B, which you just read as the probability of A given B. It's basically a formal way of asking, how does knowing that B happened change the odds of A happening? It is all about how new evidence changes the entire game. Let's make this super concrete. Say we're flipping a coin 3 times. The chance of getting 3 heads in a row, heads, 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 is just 1 in 8. Simple enough, right? But what if I tell you that the first toss was definitely heads? All of a sudden, a bunch of possibilities get thrown out the window. Our entire world of what could happen just got smaller. And in that new, smaller world, the chance of getting 3 heads is now 1 in 4. You see that? The new info totally changed the odds. Okay, so our intuition can definitely play tricks on us. A fantastic way to keep ourselves honest and not get fooled by the numbers is to just systematically map out all the possibilities. When you can see the whole picture laid out right in front of you, it's a lot harder to get misled by one flashy, attention-grabbing number. And this is pretty much how we do it. The multiplication rule helps us build what's called a probability tree, a map of all the branching paths. You just start with the first thing that can happen, you follow a path to the next thing, and you multiply the probabilities as you go. And that gives you the exact chance of that specific sequence of events happening. It's a really neat way to break down a complicated problem into simple, easy-to-follow steps. And now we're getting to the main event. We've got conditional probability down, we know how to map things out, but the tool that puts it all together, the real master key for solving our medical mystery, is the one and only Bayes' theorem. Now, don't get scared off by the formula for a second. The idea behind it is actually pretty simple, but it is incredibly powerful. What Bayes' theorem lets us do is flip or invert these probabilities. You see, the lab can tell us the probability of getting evidence, like a positive test, if you have the sickness. But that's not what you care about, right? You want to know the probability that you have the sickness if you have the evidence. Bayes' theorem is the engine that lets us flip that question around to get the answer we actually need. All right, we have built our toolkit. We've got conditional probability, we have our master key, Bayes' theorem. Now let's circle all the way back to that scary test result, and let's solve this mystery once and for all. So the most important thing is to look at all the details, not just that vague 95% accurate line. First, and this is crucial, the disease is rare. Only 0.5% of the population actually has it. This is what we call our base rate. Next, the test has a 5% false positive rate. That means it incorrectly tells 5% of perfectly healthy people that they're sick. It also has a 10% false negative rate. And what that tells us is that its true positive rate, its ability to correctly spot someone who is sick, is 90%. Okay, this is where it all becomes crystal clear. Let's just imagine we test a big group, say 10,000 people. Since only 0.5% have the disease, we'd expect 50 of those people to actually be sick, and the other 9,950 to be healthy. Now, of those 56 people, the test is 90% accurate, so it's going to correctly catch 45 of them. Those are our true positives. But, and here's the kicker, now look at the 9,950 healthy people. The test has a 5% false positive rate. That means it's going to incorrectly tell almost 500 of these healthy people, 498 to be exact, that they're sick. So let's just focus on the group of people who tested positive. We've got our 45 true positives, and we've got a whopping 498 false positives. That adds up to 543 people who all got that same scary news. And here's the absolute heart of the matter. Of those 543 people holding a positive test result, only 45 of them are actually sick. So what is your actual chance of having the disease given that you tested positive? Well, it's just 45 divided by the total number of positives, 543, which comes out to just 8.3%. That's it. Not 95%. Not even close. It's less than a 1 in 10 chance. That initial panic, it was based on a complete misreading of the statistics. So look, this isn't just some clever math trick. This is a fundamentally different way of thinking about evidence and how we update our beliefs. The answer we got feels so wrong at first, doesn't it? But it is mathematically solid, and understanding why it's right can help us avoid making huge mistakes in judgment, not just in medicine, but in all parts of our lives. This quote from the source material just sums it up perfectly. 95% of all tests are accurate does not imply 95% of positive tests are accurate. The first number is about the test's overall performance. The second number is about what a positive result actually means for you, and those are two very, very different things. This specific kind of mental error actually has a name. It's called the base rate fallacy. It's this natural human tendency we have to get mesmerized by the shiny new evidence, that positive test result, and completely forget the crucial starting point, the base rate. In our case, we forgot that the disease was incredibly rare to begin with, and that fact matters a lot. And this brings us to the final, really important question. This fallacy doesn't just show up in medical tests. You see it in news headlines, in how we judge financial investments, even in how we might judge a person based on one single thing they did. So the real takeaway I want to leave you with is this. Where else in your life are you maybe focusing on that shiny, new piece of evidence and completely ignoring the base rate?